Consider the motion of a classical particle in one-dimensional double well potential V of x is equal to 1 by 4 x square minus 2 whole square. If the particle is displaced infinitesimally from the minimum on the x-axis and the friction is neglected, then we have four options are given. Option 1 is the particle will execute simple harmonic motion in the right well with an angular frequency omega is equal to root 2. Option B, the particle will execute simple harmonic motion in the right well with an angular velocity omega is equal to 2. Option C is the particle will switch between right and left well. Option D is the particle will approach the bottom of the right well and settle there. This is a question from CSIR June 2012. First, let us check option A and option B. Here, it is given that the particle will execute simple harmonic motion. Let us find out the frequency. The expression for frequency is omega is equal to root of k by m. Now, at a stable equilibrium point x is equal to x naught, the force constant k is dou square v by dou x square. Now, at equilibrium, the net force is 0. Therefore, dou v by dou x is also equal to 0. Now, we have the condition for stable equilibrium point. Suppose x naught be the stable equilibrium point. Then, at this stable equilibrium point, the second derivative of the potential with respect to x, that is dou square v by dou x square, is greater than 0. In the given problem, v of x is given as 1 by 4 into x square minus 2 whole square. First, let us apply the condition for equilibrium. At equilibrium, dou v by dou x is equal to 0. That is 1 by 4 into 2 into x square minus 2 into 2x is equal to 0. This implies that x into x square minus 2 is equal to 0. This implies x is equal to 0 or x is equal to plus or minus root 2. That is, we have three solutions. One is x is equal to 0. Other is x is equal to plus or minus root 2. Now let us check each option and let us verify whether it corresponding to stable or unstable equilibrium point. For this purpose, let us take the second derivative to check whether the point corresponding to stable equilibrium or unstable equilibrium. Let us take the second derivative. Second derivative, that is dou square v by dou x square, is nothing but, if you take the derivative of x cube minus 2x, you will get 3x square minus 2. Now let us check the solution x is equal to 0. At x is equal to 0, the second derivative of the potential is minus 2. That is less than 0. At this point, at x is equal to 0, the second derivative is less than 0. So we can say that x is equal to 0 is an unstable equilibrium point. Now, at x is equal to plus or minus root 2, dou square v by dou x square become 4. Now 4 is greater than 0. Therefore, x is equal to plus or minus root 2 is a stable equilibrium point. So we have x is equal to plus root 2 is a stable equilibrium point. X is equal to minus 2 is also a stable equilibrium point. Thus, oscillation happens about this stable equilibrium point. Now, at stable equilibrium point, the force constant is given by dou square v by dou x square. So, k is equal to dou square v by dou x square at x is equal to plus or minus root 2, because plus or minus root 2 corresponding to the stable equilibrium point. Therefore, the value of k is 4. Now, once the value of k is obtained, the frequency omega is equal to root of k by m, that is root of 4 by m. Now take m is equal to 1, then omega become 2. So we can say that the particle will execute simple harmonic motion in the right well with an angular velocity, angular frequency omega is equal to 2. Therefore, option B is the right option.